Can you hear me?
Yeah, I can.
Okay. So these chiral catalysts can also be enzymes. Now, how do we ensure that we have just one enantiomer being formed? This is due to a concept that is called stereoselectivity. Due to stereoselectivity. And what this means is that if you have an enzyme, so enzymes have active sites, right? So the enzyme makes sure that the active site reacts with your enantiomer. And this is how it makes sure that only either the positive one is made or the negative one is made. So this is dextro and this is levo.
Levo.
Again, I'll mention clockwise, anti-clockwise. Just two more pointers for this. Print हो गया क्यों? So regional go. The enzyme ensures that only one enantiomer is formed. Let me know when you're done.
Yeah.
Okay. Now this chapter is done. Let's move on to the other one. We have 10 minutes. This chapter is also really short. This is like another section of chemistry that is analytical chemistry.
Okay.
So this has the separation techniques and everything. So in this chapter, we'll be doing chromatography, which has 3 types. Paper chromatography, which is not in the syllabus, so we won't be doing this. Then there is TLC, which is thin layer chromatography. This is in the syllabus. And then we have GLC, that is gas liquid chromatography. This is also in the syllabus. ठीक है. The second thing that we have is the second thing that we have is HNMR, also called proton NMR. And we have carbon NMR. And the last thing we have is mass spectrometry.
Yeah, I'm done.
Mm. So let's move on to the first technique, that is chromatography. So here's the diagram for it. This is the whole setup. Okay. We have our chromatography paper attached. This is your solvent. This is also called mobile phase. Why? Because this is the part of your setup that moves, right? Now, when you put your paper in your solvent, it starts to absorb the solvent, right?
Yes.
So wherever it stops absorbing it, you make a thin line with a pencil. This is your baseline. Why do you not make it with ink?
Because that can smudge.
Yeah. Also, the chemicals in the ink will mix with the solvent, right? So you won't get good results for your chromatography. So here you place your solution, label it as X. Now, when you're done with the whole chromatography process, what happens is all the components of your solvent are separated according to the retention factor or the retardation factor, right? So we'll get
Yes.
into what that factor means. But for example, you have A, B, and C separated here. The line till where your solvent actually travels is called the solvent front.
Nine.
Okay, this is your solvent front, and this will be the distance traveled by A. This will be the distance traveled by B, and this will be the distance traveled by C, right? So in MCQs, what they usually do is they are going to probably give you this distance. They're going to give you this distance, and they're going to give you this distance. Okay? Now you need to remember, and if they ask you, okay, what's the retardation factor for C, right? So
Yes.
what do you do? Distance traveled by C over the total distance traveled. I will I will discuss this in detail, But when you need the distance traveled by C, what a lot of students tend to do is they take this value, which is wrong. The distance traveled by C is what?
Oh, the CD value, the
This
whole,
whole thing, right?
yeah.
This whole thing is the distance traveled by C, not just this. So what you need to do is add this distance and this distance to get
Mm.
this whole distance, right?
Yeah,
So make
yeah.
sure you keep this in mind while you're doing MCQs or basically any question that has chromatography, right?
Okay.
Now we move on to the retention or the retardation factor. This is denoted by RF, and the formula for RF is, for example, we're taking out the retention factor for A. So the formula is distance traveled by spot A upon the distance traveled by solvent front. And so this whole value for RF will
Mm.
always be less than 1.
Yeah.
And why is that? Because the numerator here will always be lesser than the denominator, right? You can't have your
Yeah.
spot A traveling higher than your solvent front, right?
Mm-hmm.
Which is why this is the numerator is lesser than the denominator, right? Which is why your retardation factor or your retention factor will always be less than 1. It will
Yeah.
always be in 0.5, 0.25 or something. Okay?
Mm.
Now, what does the retention factor signify? This is your paper. This is your solvent. A is here. B is here. So your solvent front travels 10 centimeters.
Mm.
A travels 5 centimeters.
Mm.
And B, for example, travels 8 centimeters.
Mm.
Now, I tell you to find the retardation factor for B.
Mm.
What will you do?
8/10.
Right. So this will be 8 over 10, which gives you 0.8. And for
Mm.
A is going to be 5 over 10, that gives you
0.5.
a 0.5. Okay? So this is a smaller RF value.
Yeah.
This is a
Great.
greater
Mm.
RF value. Now, what do these RF values signify is they tell you how polar your solvent is, by how polar your
Mm.
component is. So this the one with the smaller RF value is more polar, and we'll discuss why. First, let's write notes for this. Acha, this too is from O levels. You must be knowing that the one that
Yeah.
travels more is more soluble, right? More
Yeah.
soluble in the solvent that you've used. Okay, so what's more soluble here?
0.8.
Right. So this is more soluble. This is less soluble. B is more soluble in the mobile phase, whereas A is less soluble.
Mm.
So what we can do is just copy the notes. Since we're out of time, I have another class after this. So just copy the notes and we'll do the explanation part and the rest of the techniques, they're really short, in the next class on Tuesday, right? Also,
Yeah.
don't forget, just a reminder, just let me know the times when you're not free, right? On WhatsApp.
Okay, fine.
Is more soluble in the solvent, non-polar, and travels up higher. Right, let me know when you're done.
Yeah, I'm done.
Okay, good. Any questions?
No.
Okay, perfect.
Thank you.
So I'll see you on Tuesday then. Take care.
Sure.
Bye.
Bye.